Hello students, welcome back to the next video on digital communication. Myself Gunjan Mittal Roy in the Department of Electronics and Communication Engineering in Jamtech, Greater Noida. In the previous video on Unit 2, we have completed random variables and in that we have covered the properties and CDF, PDF, definition of random variable, sample space, probability, and its joint PDF, joint CDF, moment, mean, and so many other aspects. Now in this video we are going to discuss on the next thing in random variables, which is random processes. So what is the difference in random variable and random process? So when a particular random variable, which is defined by a sample space, within a sample space, includes a time measure also. That means when the time is the next dimension which is added to a random variable, then that random variable can be termed as a random process. For example, if we talk about a random variable where we have considered tossing of a coin, throwing of a die. So if tossing of a coin not only is a random variable, but it is also a process which takes some time. Similarly, throwing of a die takes some time. So when the time dimension is also added along with the original random variable, then that random variable becomes as a random process. So if there is a sample space having n number of samples, so for each n number of sample there would be n random processes, which is defined by a graphical pattern in this diagram. These are denoted by the function xn1 nt, xn2t, xn minus 1t, xn plus 1t, and so on. So the x of t, so the random process is basically determined by x of t. It is defined as capital X of t, where capital X of t includes all small x, t and x1 of t, x2t, and so on. So the random process is determined by a random time function. So random process xt is classified in following ways: first order stationary random processes and the second order stationary random processes. So the first order random processes includes probability density function, and it may have any time shift. It is not at all dependent on any particular time shift from the origin, but it depends on the PDF function, probability density function. So if xt1 represent a given value of a random function at time t1, then we define the first order stationary function that satisfies the following equation. So the first order stationary function is given as fx of xt1 equal to fx of xt1 plus tau, where tau is a dummy variable which is added and it is showing the shift of time. So there can be any shift of time, but the PDF remains same. So the physical significance of this equation is that our density function is completely independent of T1, which is the time shift tau, as I mentioned. So for the first order stationary function, the mean is constant or independent of any time shift. So this is another property, that the PDF, the first thing is that the PDF should remain constant, PDF should remain same regardless of any time shift. And the second meaning is that the mean remains constant, because the mean is nothing but x fx of x dx integrated over minus infinity to infinity, where fx of x is nothing but the PDF. Now we come to the second order stationary function. So the second order stationary function in this second order density function does not vary over any time shift. So in this also the probability density function does not vary over any time shift applied to both values. So if the two values are xt1 and xt2, then also fx of xt1 comma xt2 is given as fx of xt1 plus tau comma xt2 plus tau, where tau is an equal arbitrary shift. So the PDF function does not vary for any time shift, but it has to be a constant or fixed value or same value for both functions t1 and t2, xt1 and xt2, and that shift is given by the time function tau. Okay, so for a second order stationary process, we need to look at the autocorrelation function. And what is that autocorrelation function? We will discuss it in later presentations. For the time being, here we can express that autocorrelation function is given as rxx tau, rxx t comma t plus tau. It is basically showing the relationship of a same random function x, fx, with its time shifted function. So it is given by the product of expectation of xt, the time function xt, the random function xt, and its time shifted version xt plus tau. So the product of expectation of xt and xt plus tau gives the relationship of autocorrelation, and which indicates that autocorrelation function is independent of time. Now, wide sense stationary function. What are wide sense stationary function? So for a function to be wide sense stationary, the two properties must be satisfied. The first property is that its mean or expectation value should be a constant value. It should not be a function of time. And the second thing is that its autocorrelation function should be independent of time. It should be dependent only on tau, which is a dummy variable. So if the two properties are satisfied, then the random process is called as wide sense stationary. And we can also conclude that the second order stationary functions are wide sense stationary, because in second order stationary functions also we have taken both these conditions, but the vice versa is not true. Now the time average or ergodicity. Ergodicity is the time average is equal to the ensemble averages, and the time average is given as the limit t tends to infinity 1 upon 2t, where t ranges from minus t to t, function dt. The time average is taken over all time, because as applied to random process, sample functions of processes are presumed to exist for all times. So these are defined for all times. So this is showing the sample space, as I mentioned in the previous slides also, that the sample space is given by S, having number of observations denoted by Sn, Sn minus 1, Sn plus 1, Sn plus 2, and for each sample or for each observation, for each experiment, there is a random process given as xn t, xn plus 1 t, xn minus 1 t, xn plus 2 t, and so on, depending on the number of observations in the sample space. So here xt is the random process, capital Xt is the random process, and it is the sample of a random process. Small xt is the sample. Capital Xt is the random process overall, and small xt is the sample of that random process. So it is showing here that we define mean value or expectation by x bar equal to a of xt, and the autocorrelation function is defined by rxx tau. where mean or x bar is a of xt, which is limit t tends to infinity 1 upon 2t minus t to t xt dt. And autocorrelation function is given as a of xt into xt plus tau. It can also be determined in the form of the integration function. Okay. So the expectation and autocorrelation functions are determined first. And expectation and autocorrelation. Expectation is determined as e of x bar, where e of x bar is a of xt. So e of limit t tends to infinity 1 upon 2t minus t to t integration xt dt. E can also be taken inside the integration part. So limit it becomes limit t tends to infinity 1 upon 2t minus t to t integration x bar dt, and it is also equal to x bar of 1, which is equal to x bar. So the expectation of x bar is equal to x bar, and similar way we can derive the autocorrelation. Expectation of autocorrelation is also equal to only autocorrelation. See, we can observe here that e of rxx tau comes out to be only rxx tau. So the expectation of x bar is equal to x bar mean value, and the expectation of autocorrelation is equal to the autocorrelation. Thank you so much.